Alright, here we are in part 3 of the practice test. Learning target D, I can calculate it and determine the frequency, wavelength, and energy of electromagnetic radiation. So to do these on the test, you'll have the electromagnetic spectrum chart in some common units. You'll probably have this black and white type of picture. I'll also have this one up right here just because it's in color as well. And it's backwards of this one, so it makes it a little more challenging and a little more fun to read. So let's first do everything with the EM spectrum chart, and then after I do it with the chart, then I'll also do the mathematics for several of them as well. So first of all, it says it takes 13.6 electron volts, or 2.18 times 10 to the negative 18th joules, to remove an electron from the lowest state of hydrogen. In what region of the EM spectrum is this radiation which can accomplish this? So first we need to find either 13.6 electron volts, notice electron volts are given right down here, or joules, 2.18 times 10 to the negative 18th joules. So here's times 10 to the negative 18th, which is approximately 13 electron volts, because we're a little bit to this side, we're a little bit larger than that. See how it's 2 times 10 to the negative 18th? And this would be 10 to the negative 15th, so a little bit larger, would be somewhere around in here. It says 13 electron volts, would probably be right next to this 10, because there's 100 right there. So following this up in an approximate way with kind of a straight line right here, we'd be able to get to the region of the electromagnetic radiation, which would be right down here. So we'd be a little bit to the right of the UV, a little bit to the right of the visible and a little bit before the UV. But you know that the visible is actually a very, very small part. But just to make sure, go ahead and go up here to the wavelength, and we're at approximately 10 to the negative 7th, or 100 nanometers right here. And then you could flip over to this chart right here, and you could see that the red, orange, yellow, green, blue, indigo, violet goes from 700 nanometers down to 380 nanometers. And remember, we found right here that it would be approximately 100 nanometers. So going less than 380 nanometers means we'd go a little bit to the right here, and a little bit to the right of the visible spectrum is what's called the ultraviolet radiation area. So that would be in the UV radiation area. Alright, secondly, a radio station broadcasts with a frequency of 95 megahertz. A megahertz is 10 to the 6th per second, or hertz. Remember, a hertz is the same as a per second, or the fancy way to write it is seconds to the negative 1. What is the wavelength of this radiation? So using the EM spectrum chart, we need to find hertz, which is right here, the symbol Greek letter nu in HZs right here. And we need to find 95, or I'll rewrite it this way, 95 times 10 to the 6th hertz, right? Because a megahertz is 10 to the 6th. Or, if you wanted to write it in correct scientific notation, it would be 9.5 times 10 to the 7th. Or since 9.5 is pretty close to 10, it's like 10 times 10 to the 7th, or 1 times 10 to the 8th or so. This might be easy to find on here. So looking at hertz, here's 10 to the positive 19th, all the way down here to 10 to the 8th. Oh, okay. So 10 to the 8th, we're a tiny bit smaller than that. We're right here. So we should follow up right here, and we should find a wavelength somewhere between 1 and 10, somewhere in there. That's pretty close to, between those numbers. So to calculate the wavelength, though, we could go ahead and we could use the equation C equals lambda nu. We usually write it as a triangle like this. And if we're looking for the wavelength right here, we could write wavelength is equal to C over nu. C, of course, is 3 times 10 to the 8th, and that's meters per second. And of course, you get a chart with lots and lots of information on it. And C is given to you on here multiple times, 2.999 times 10 to the 8th meters per second, listed right there. You get this information on there. You even have the equation right here, C equals lambda nu. It's not in a triangle, but it tells you which one's the wavelength, which one's the frequency. And then nu is the frequency, and you can go ahead and put in 9.5 times 10 to the 7th. And that would be in 1 over seconds, and then the seconds cancel with the seconds, and you'd end up with your frequency in meters right here. And so dividing those two, you'd end up with 3.15 meters, which we estimated it'd be somewhere between 1 and 10, and 3 is definitely somewhere between 1 and 10. And so that would be our wavelength in meters for number 2. Number 3, of the following, blank radiation has the shortest wavelength. So you can find this several different ways, but I think looking at a chart like this is helpful because it's actually got the waves right here, and it actually shows them getting shorter and shorter or closer and closer together. And the chosen ones in here are ultraviolet, X-ray. Oh, and we can already see that X-ray are shorter wavelengths. You can look at the numerical values here too. Here's 10 to the second. Here's 10 to the negative 10th or so. Much, much smaller. Radio waves, which are over here. Microwaves, which are right in the middle. And then infrared, which is a little bit shorter. And so you can see that X-rays are definitely the shortest wavelength right there. You can also see it on this chart right here, where you've got X-rays listed right here, and here they are in nanometers, and you can see X-rays are about 1, or 10 to the negative 9th, just like we said they were about 10 to the negative 10th, so we're close on the other side. Here's UV, here's visible, here's IR, here's microwave, here's radio, and you can see that they get 10, 100,000, 10,000, 100,000. They just get bigger as you go this direction. So this side of the chart is just as good at finding that as well. So X-ray would have our shortest wavelength. Be ready to answer a question about what the longest wavelength is too. So then just be a good reader of the chart on which direction it goes. Number 4, the bond energy of X to X, so this bond right here that holds those two elements together, is 378 kilojoules per mole. What is the wavelength in nanometers of the photon that has just enough energy to break the bond of this element? Well, fortunately for us on this chart, we're given energy in kilojoules per mole right here. And we're told that the energy is 378, and then we could compare that to find a wavelength and get an approximate value. So 378 would be somewhere between 100 and 1,000 right here. So 300 would be somewhere in here probably. And we could follow that up, and then we could find a wavelength right in here, and it looks like it's somewhere between 100 and 1,000 nanometers, or somewhere between 10 to the negative 6th or 10 to the negative 7th. So it'd probably be something times 10 to the negative 7th, and let's see if we get that number when we actually do the math. So the bond energy right here would be found by using the equation E equals H nu, and if you don't remember that equation, you can look it up right here on your little equation chart. Energy right here of a photon, and then they put it actually in the substituted form right here, hc over lambda, because of course nu right here is equal to c divided by lambda, and so if you replace c divided by lambda, you end up with h times c divided by lambda, and that can be really handy because we're actually looking for the wavelength right here. So once again, here's that equation right here on your equation chart. We're looking for the wavelength, so let's solve this equation for the wavelength by multiplying both sides by lambda and then dividing both sides by e, and then we'll get our e's to cancel, our lambdas to cancel, and we end up with the equation lambda is equal to h times c over e. Nice for us, h, Planck's constant, which is given to us as 6.26 times 10 to the negative 34th. C, which is given to us as about 3 times 10 to the 8th, is multiplied together for us on this chart, so you never have to do it. It's equal to 1.9865 times 10 to the negative 25th joules times meters. They already did the unit canceling for you there as well, because of course Planck's constant is in joules per second, and then C is in meters per second, so you get the canceling of those units. And then E that you have to put in here has to be in joules, of course, because you want to end up with meters as your answer. So this is 378 kilojoules per mole, so we're going to have to convert that to regular joules. And when you go from regular joules to kilojoules, of course, it's times 1,000, so we would end up with 378,000 joules, and that's per mole. And we want to know the wavelength of one photon of this, because it says wavelength of the photon. And of course, in a mole of photons, there are 6.02 times 10 to the 23rd. And so in 1 mole of these photons, there would be 6.02 times 10 to the 23rd of these photons. Don't get that 4 mixed in there. That just happens to be a page number on here. So taking this and plunking it into your calculator, careful of this times 10 to the negative 24th. Don't forget to divide those two and then divide that whole thing. You end up with a wavelength of somewhere about 3.16 times 10 to the negative 7th meters. And let's see if that's close to what we predicted. I think we said it would be somewhere around 10 to the negative 7th. Yep, something times 10 to the negative 7th. And it turns out to be 3 times 10 to the negative 7th meters, which is the wavelength. And this happens to be in meters. And then to go from meters to nanometers, remember that there are in 1 meter 10 to the 9th nanometers, so multiplying it by 10 to the 9th, add those exponents, you get 10 to the 2nd, so it would be about 316 nanometers or so. Most of these types of questions, you can just get an approximate answer right here, and it will be absolutely fine. But I did the math as well. All right, we're on to number 5. The energy of a vibration of a molecule is 3.65 times 10 to the negative 20th joules. What is the corresponding wavelength of electromagnetic radiation in meters? So we're given an energy in joules, and you can find the energy in joules right here, and it's times 10 to the negative 20th. Here's times 10 to the negative 21st. Here'd be negative 20th. We're a little larger than that, so 3 times would be approximately right there, 10 to the negative 20th. 3 times 10, almost 4 times 10 to the negative 20th joules. And it wants to know the wavelength. And so if we'd slide this up here to the wavelength area, you'd probably end up with a nanometers of somewhere between 1,000 and 10,000. Okay? If you found it in meters, it would be some number times 10 to the negative 6th, maybe some big number even, 5 or 6 times 10 to the negative 6, because we're getting pretty close times 10 to the negative 5th right here. Well, if you want to see the math for that, to see if we get close to somewhere between 1,000 to 10,000 nanometers, that's what I got from the chart right here. Let's do the math. And when I do this, I can use the equation E equals hc over lambda, and I want to solve for lambda once again, and so solving this, it would be lambda is equal to hc divided by E. Hc we know is on the chart right here given to us, 1.9865 e to the negative 25th joules times meters. And then the energy is given to us right here in joules, so 3.65 times 10 to the negative 20th joules. The joules cancel with the joules, and I'm left with meters. So let's see if we get close to this when you punch these numbers into the calculator. Let's see. You get something times 10 to the negative, oh, that's in nanometers. Shoot, I guess I better do it on my calculator here, and then you can watch me and see if I make a mistake on this. 1.9865 enter exponent negative 25th divided by 3.65 enter exponent negative 20th, and enter, and I get 5.4 times 10 to the negative 6th. And that would be in meters. And let's see, I said it would be something times 10 to the negative 6th, and I said it would be a bigger number times 10 to the negative 6th because we're right up here. And lo and behold, that's about what it is, 5.4 times 10 to the negative 6th meters. And then if I wanted to convert that to nanometers, remember that in 1 meter there are 10 to the 9th nanometers. Add those exponents, I'd have about 5,400 or so, which is between 1,000 and 10,000 nanometers, just like I said it would be. All right, we'll come back in another video for more of these problems.